All right, so we're going to turn to degrees of simple extensions. So suppose, because all the extensions that we've seen are actually simple, uh, and you kind of have to work to prove that an extension is not simple. Um, and you're free to ask me about an example if if you're interested in that. But suppose we have a simple extension. There's two types of simple extensions again, and those are transcendental, where you add something like an indeterminate, or you add in like e or pi to q, something like that. So if it's transcendental, then the degree, well, we saw that you sort of get infinitely many things, infinitely many copies of k, just for like polynomials in alpha. But then have to look at rational expressions in alpha, and this is a big, this is big. So this is infinite. It's actually, if you care about cardinalities, this is countably infinite, but nevertheless it is infinite. If it is algebraic, which is the main type of extension that we're going to be looking at, then the degree of k of alpha over k is the degree of m sub alpha, where m alpha is the degree, or sorry, is the minimal polynomial of alpha over k. Okay, so the degree is literally the degree of a polynomial. All right, so that's why one of the reasons why we use these words, this word. Okay, so let's prove it. Proof. Well, if alpha is transcendental, then well, all of these elements, 1 alpha, alpha squared, all the way up to alpha to the n, and keep going, these are all linearly independent. Because if they were linearly dependent, you would have an algebraic, well, you would have a polynomial that alpha was a zero of. So that's that. So there's infinitely many terms in a basis. Okay? In fact, again, it's countably infinite, but infinite. Uh, and then if it's algebraic, with minimal polynomial m alpha, then we proved a theorem. We proved that k alpha over k is isomorphic as an extension to k join t mod m alpha over k. And that isomorphism, it's not relevant for the proof, but the isomorphism from this quotient of polynomials over k to k alpha was evaluate at alpha. So that was take a polynomial, plug in alpha. Okay. All right, and we showed that a basis for this guy, the left field, the quotient ring, which happens to be a field, is 1t squared all the way up to t to the degree of m alpha minus 1. Okay, so that's the t to the degree of m alpha minus 1. That is, what we did is we showed that every element here has a unique representation of degree less than m alpha. Okay, and that's equivalent to what I just said here. Okay, how many terms are there? Well, there's 1 up to the degree of t, powers of t up to the degree of m alpha minus 1. So I'm counting the degree of m alpha many terms. Okay, so there are the degree of m alpha elements here. And any field isomorphism is actually a vector space isomorphism. It's a linear transformation, and so since ev alpha, evaluation alpha, is an isomorphism, it's a field isomorphism, It sends a basis to a basis. And what does it do to these t's? It plugs in alpha into them. So this is a basis for k alpha as a k vector space. Thus, the degree of k alpha over k has, again, how many elements are there? The same as before, the degree of m alpha. All right, so for example, we saw that the min poly of cube root of 2 over q is t cubed minus 2. Why is that? Well, t cubed minus 2 is irreducible over q by like Eisenstein's criterion, and it's monic, so therefore is the minimal polynomial. This minimal polynomial has degree 3. So this is m cubed root of 2 of t, and the degree of m cubed root of 2 of t is 3. So if we add in that guy, the cube root of any of the cube roots of 2, let's say the real cube root of 2 for this example, we should get 3. And in fact, we saw that, so we already know this. In fact, we saw that q would join the cube root of 2. We can write as p plus q cube root of 2 plus r cube root of 2. And this was something that you investigated in probably all your homeworks at this point. It's a very important example. So that's an example of using it. You just have to find the minimal polynomial and then look at the degree of that guy.